Hello, my name is Pamela. I am going to be sharing with you today the Basic Statistics 5 module on continuous probability distributions. A little bit about myself before we start. I have a bachelor's degree and a master's degree in applied statistics, and I grew up in the United Kingdom and I now live in Southern California. And I look forward to sharing these slides with you. Let's get started. For this module number 5, we are going to be looking into recognizing the difference between a discrete and a continuous probability distribution. I know you saw a little bit about that before in an earlier module. We'll then be looking at the uniform probability distribution, how to recognize it and applying it in real life applications. And also we will be looking at the normal probability distribution, how to recognize it, its applications, and how to convert it to a standard normal distribution. Before we get started on our work, we want to make sure that everybody has this data analysis button installed on their computer. I'm going to show you how to get that if you don't have it right now. So first of all, let's check whether you have it already installed. I'm going to take you to look at my Excel. I have a blank worksheet available here. So hopefully you can see this, and I'm going to, if you go to the data tab and look to the end here, you can see there's this data analysis button. What it does actually is it gives you all of these statistical options for doing some basic statistical tests. So that's going to be something that's handy to have. I'm using a Mac version, so I'm going to take you through how to look into installing it here. But if you have a different version, that's fine. I'll show you that also. So this is Excel add-ins. You can select these two here, put a check mark next to each of these and press OK. And then you should be able to go to the data, look at the data analysis button right here. You have it right here, ready to go. And then go back to our PowerPoint, and I will show you. This again is if you want to pause the video and use the instructions here to install on the Mac version of Excel, you can do that. I have instructions right here for Windows. You may even find you're watching it in a few years' time and these instructions are a little out of date for the version you're using, so that's fine too. You can go to the Microsoft support website and type something in the search like analysis toolpack in Excel, and it's going to give you the most current instructions. If you don't have any Excel available to you, you're still going to be able to watch these videos just fine and learn something from them, so don't worry about that. This is just going to give you an opportunity to be hands-on and practice with some of the tools that are available to you. Okay, we're ready to get started. When you first get your hands on a data set, it doesn't tell you very much when it's just this big spreadsheet full of numbers, and you might want to think about getting some insight into what your data looks like visually, because most people's brains, they process pictures far faster than just words or numbers on a page. So doing this can help you identify the shapes or the distributions, and it can help you very quickly spot any missing data or outliers. The outliers are values that are very different than any other point in the data set. And those are things you might want to drill down on and do some further investigation to find out whether they're a typo or they're real values, which can happen. So there might be a little bit of data cleaning to do, and doing this exploration of your data set is going to help you do that. So it can even give you some other questions you want to ask, some ideas for hypothesis you would like to test. But I always find that, especially when you've got a really big data set, the exploration and the graphing and getting a feel for the variables is definitely a good first step to take. In a discrete probability distribution, X is going to be something that's countable. It will be something like you'd be doing an experiment where you're throwing balls into a basketball hoop, or you're counting the number of texts received by some group of people, or the number of eggs laid by a chicken, to quote this example. Something like that, where you've got whole numbers, generally like 1, 2, 3, 4, 5. If you are seeing numbers that have decimals after them, lots of decimals, then you're not generally looking at a discrete distribution. In fact, I can't think of any examples where that would be the case. So you can't have half an egg. You can't have half a throw into a basketball hoop. So that's the kind of evidence you're looking for when you're labeling it with this discrete probability distribution X. Now, I've said here, and it's the case in most instances, that it's finite. It's a finite number. It can be that it is infinite, and that would be something like if you're measuring the number of coin tosses until you throw a head, then theoretically, although unlikely, but theoretically, you could never throw a head. So in that case, it's countable, but also it's infinite. Now, when you are seeing a graph of this kind of thing, it's going to be the number X along the bottom, so all the possible outcomes that you have in your experiment, and then up on the y-axis, you're going to see the probability. So you'll see usually a number of rectangles as your graph. I have an example here that I've picked out, and so we have a chicken, and every week she lays some number of eggs. I'm going to list all the possible outcomes, which is this column here, X. Got 0, 1, 2, 3, 4, 5, 6, and 7. And that's, in my experiment, that was all the possible outcomes. And then I'll go about collecting a little bit of data, and then I know the probability of each of those things. I can assign a probability to each of those X values. Now, we know it's discrete because we have discrete numbers. Like I said, you can't have a chicken laying half of an egg, can't have any, like a third of an egg or anything like that. It's always going to be these whole numbers. And thinking about what we saw on the previous slide, we were talking about if we add all the probabilities, we would get 1. Now we look at this chart I've written here. If you add all of those probabilities, you're going to get 1. Try it out. And if we look at all the probabilities, we're going to see also that they're all between 0 and 1. So it is consistent with the information we saw on the previous slide. Now let's look at continuous probability distributions. In this case, X is not countable and has an infinite number of values. It can be anything that is measured, like height or weight or distance. Usually you're going to use some kind of measuring tool for that. So maybe a weighing scale or a ruler or something where you can measure in partial amounts. It's going to be continuous if there's no gaps between the values. X will always be able to take any value greater than 0, and the area under the entire curve is equal to 1. Now, I was talking in the last slide about how you would have something along the bottom and the probability along the y-axis, and it was all going to be rectangles. In this case, that's not true. You're going to have a continuous curve across the graph, and you're not going to be able to split it up. So you're going to have to base all of your math on or all of your hypothesis on the probability of it being between two values. You're not going to be able to say the probability of X equals 6, for example, because that's going to be one line, and you're going to be basing all of your math on the areas under the curve. Now, two examples that you might have heard of in statistics of the continuous probability distribution is the normal distribution and the exponential distribution, and they're very common in statistics, and we'll be looking at some examples of those in slides as we continue this lesson. The uniform distribution is very easy to spot, and you'll know it right away by its recognizable rectangle shape. The reason for the shape is that all of the outcomes in a graph, it's going to have an equal probability. So on a graph, it's going to look the same all the way across. The discrete uniform distribution is a probability distribution where we have a finite number of equally spaced values that are equally likely to be observed. For example, if we have a 6-sided die, then we have the same chance of rolling a 1 or a 2 or a 3 or a 4 or a 5 or a 6. And if we were drawing a graph of that, we're going to, along the x-axis, we're going to write down 1, 2, 3, 4, 5, 6. And the probability is always the same, it's a 6. So we are going to write the number 1 over 6 in the y-axis, and then along this line, we're going to have a rectangle going up between the 1 and the 2, which is 1/6. The next rectangle will be exactly the same, and so on, and it will go all the way from 1 to 6 with these equal height rectangles. You have a box of 12 eggs, and you need to pick one out for baking. The probability of you picking any single one of those 12 eggs is exactly the same, and that probability is, yep, you got it, 1 out of 12. And as you can see, every value in the interval is equally likely to occur. The area under the graph of a probability distribution is equal to 1. You might also see a uniform probability distribution that is continuous. When we had a discrete uniform distribution, the outcomes were things like 0, 1, 2, 3, 4, 5. They were all discrete numbers. In this one, you can have a continuous pattern where it takes values everywhere in a whole range. So let's look at an example. If we had waiting times, perhaps we own a car service shop and we want to know the length of time it takes to change the oil in the car, maybe to help the business figure out how far apart to schedule the appointments for the maintenance. So we have, in this example, Fix-It Cars finding that the amount of time a serviceman needs to change the oil in the car is uniformly distributed between 14 and 25 minutes. Could it be less than that? Yes, it could, but in the data we collected, we did not find anything below 14. So that becomes our minimum value that X can take on. And then we found that there were no oil changes that were more than 25 minutes. So that becomes our upper bound based on this particular serviceman. So what we're going to do, I'm going to get you a graph here so you can have a look. Annotate. So let's choose X to represent the time to change the oil in minutes. So I'm going to draw a graph right here. Sorry, that's not very straight. And we'll put X along the bottom. This will be A, which is our minimum value, which we have as 14. And then our upper value is going to be B, and that was 25. And it's a continuous probability distribution, so we can draw this rectangle here. And we know that the area under this curve is going to be 1. And this value all the way along here, because we know it's uniformly distributed, so we know it's the same all the way across. This we're calling f of x. Now, how do we figure out what this f of x value is? Well, what you can see here is the area under the curve is 1, and we don't need to do any integration or anything in this case to find out what this is, because this is a rectangle. So once we've recognized that that's the case, we know that the area of a rectangle is this distance times this distance, base times height, right? So if we do, in fact, I can do this with a text button. Okay, so then we know it's base. In fact, no, sorry. The base calculation is going to be 25 minus 14. So we can do 25 minus 14, put that in parentheses, and then multiplied by the height, which is f of x. And then that's going to equal 1, because that's the area. And then it follows that 1 divided by 25 minus 14 equals f of x. Or in more general terms, it would be that b minus a times f of x equals 1. So it would be 1 divided by b minus a equals f of x. And then you will have this value . So in more general terms, the notation for the uniform distribution is just like this. X is uniformly distributed between the values of a and b, where a is the lowest value of x and b is the highest value of x. Then the probability distribution, the probability density function, sorry, is f of x over 1 divided by b minus a for the range a is less than x, that's less than b. So for this example, we saw on the previous page with the oil changes, this x is uniformly distributed between 14 and 25. And then f of x is 1 over 25 minus 14 between the values of 14 and 25. And then these are the formulas for the theoretical mean and standard deviation. What I want you to do now is do a few exercises, see if we can figure out the answers to these questions. So we'll want to find the probability that a randomly selected car oil change takes more than 20 minutes. The probability that a randomly selected car oil change takes less than 15 minutes. And I want you to find the theoretical mean and the standard deviation. On the previous page, we saw the formula for the mean and the standard deviation, and I'm going to give you a clue about the first two. It's remembering the shape of the uniform distribution, and then once you had a go, maybe we can move on to the next page and go through those. Okay, hopefully you had fun doing some of these problems. I am going to take you now through what steps I would go through to answer those. So what I'm going to do, and what I do in every single time I have one of these kind of problems, is I draw a graph like so, and I would label the minimum value, which we have 14, and also the maximum value is 25. And what I'm going to do is, I know that the shape is going to be like this here because we have a uniform distribution, and because we're looking at 20, I am going to go ahead and 20 will be around here. I'll label that, and the area we want to find is this one. So shade that in there, type 20. And there we go. This gives us a very good picture of what we're looking at. And I'm going to also write f of x up here because that is what we're looking for, first of all. So we do, to get the probability all the way along this line, which is f of x, we would do the 25 minus the 14, and it will 1 over that number will give us that f of x value that we're looking for. So 25 minus 14 is 11, and then 1 over that will give us 1 over 11, so f of x is 0.09. When we're looking at this area here, we're still looking at a rectangle right there, so we're going to do the base 25 minus 20, which is 5, and then times the height, which is f of x right here, and that will give us 0.45, and there you have it, that's your answer. So if we went back quickly to I'll just close this. We went back quickly to the question, find the probability that a randomly selected car oil change takes more than 20 minutes. Our answer is the probability of 0.45. Okay, moving on to the second question, we'll do it in a similar way. Get my annotation button here and let's draw another graph. So I'll make it a little bit smaller. Okay, again, I'm going to label with the 14 and the 25. I'm going to do a rectangle. A little long there, should be okay. And I'm looking now at the probability of x being less than 16. 16, not too far away from 14, so it's going to be maybe this area. Isn't obviously perfectly to scale. If I had a graph on paper, I could do it that way, but we'll just roughly shade this area, and we calculate it in pretty much the same way. I'm just going to label that for you so you know that that's, move it a little bit long, 16 there. Okay, so again, we're looking at a rectangle, and our f of x hasn't changed. That's still going to be 0.09 because that's calculated with the 25 and the 14, and that's the uniform distribution all the way across. So we're going to do 16 minus 14 times the 0.18, and as we would expect, it's a less number than, or a smaller number than this one, and our probability turns out to be 0.18. And there we have it. Hopefully some of you got that in the questions. If not, no worries. You can always work through these problems on paper. I find it helps to learn that way. So I hope you're writing these down. Okay, now we did see some formulas on the previous page for calculating the theoretical mean and the standard deviation. So for this problem, the theoretical mean and standard deviation to 2 decimal places are calculated by plugging these numbers into the formulas. 14 plus the 25 divided by 2 is 19.5, and then the standard deviation, I need to change that. The standard deviation is 25 minus 14 squared over 12 equals 3.18. What we have here is the normal distribution. It's also known as the bell curve or the Gaussian distribution, and it is a very frequently used distribution in statistics. It's shown down here in this drawing, and we have a variable x along the bottom, and we would have f of x, the probability function, along the y-axis, and the f of x is what would give us this height of the curve. Now, the normal distribution is continuous and can take any value between minus infinity and infinity, literally any value. And mu is one of the parameters. There's 2 parameters. Mu is the mean and also the median, because it's right here in the middle. And you would also have the standard deviation, sigma. And we can see mu here right in the middle, and the normal distribution is symmetrical around that center mean. And so if x is a random variable that has a normal distribution with a mean mu and a standard deviation sigma, we would write this as x is normally distributed between mu and sigma. Now, I just wanted to point out as well that sometimes you'll see this written in a slightly different way with this second term as the variance. So then it would just be mu and sigma squared. Thinking back to what we were previously looking at, the uniform distribution, that allowed us to see a couple of things. The first being that the area under the graph of the probability distribution is 1. And also that probabilities can be determined by identifying the corresponding area on the graph. Now, when we were looking at the uniform distribution, we had that rectangle shape, right? So it was very, very easy to calculate the area because you could just use the base times the height. Now with the normal distribution, it is a little more difficult because you're going to have to use integration to find that area under the curve, but the principle is the same because the area under the curve still equals 1. So luckily, we do not have to do any math integration. We can use statistical tables, which is one method. And what we're going to be using is technology. We're going to use Excel for this course. The standard normal distribution is so called because it has a mean of 0 and a standard deviation of 1. So this along the bottom on this drawing here, you can see what we call the z-score. And we think of that as a measure to tell us how many standard deviations we are from the mean. So you can see here we would go to 1 standard deviation from the mean, here would be 2 standard deviations, and here 3. And you can see just looking at this picture that within 3 standard deviations of the mean, that's pretty much all of the area covered right there. We would write that as z is normally distributed between mu and sigma. And again, the area, the probability, is the region under the curve and can be found using software or tables. What I want you to do is go ahead and open up your Excel spreadsheet so that you can have a go at maybe finding some of these areas under the normal distribution. So we're looking at z-scores. Along this bottom x-axis is the z-scores. I've just put a 0 in there. That's where the mean would be. And this is going to be your negative z-scores to the left, and this is your positive to the right. And when we type in this function, norm.s.dist, we will be able to put the z-score in, and that will return the area to the left of that value. So if you had this value, we're going to try, for example, here is 1.3. So that's going to be over to the positive side a little way, and we draw a line here, and that will give you this area under the curve. It's always 100% of the time going to be true when you're working with a normal distribution, so don't even worry about that. It's always true. And I usually write the z or the probability to 4 significant figures when I'm doing these, which is what it used to be when you had the statistical tables. So yeah, let's go ahead and put a few things in Excel. It'll just get you used to typing something into Excel and returning the value. You can play around with a few negative ones. They will give you a lower value here, do a few positive ones. And when you type it into the cell in Excel, you've got to type the equal sign beforehand. So you put equals norm.s.dist, and then you would do the parentheses or brackets and the z-score, the comma, and then true. Close brackets, press enter. That will return your value. No integration needed. Now we're going to look on the next slide at the conversion that allows us to standardize any type of normal distribution into a standard distribution. So given that we don't always have a mean of 0 and a standard deviation of 1, we've got to find out a way to find that z-score when we have a different mean and standard deviation. So what we're going to do in anything like that is we're going to sketch the normal curve like I always do. We're going to label the mean and any X values that you want to test and shade the relevant area. Then you will use this formula, z equals x minus mu over standard deviation, to find the z-score, and then you know how to find the area of that shaded region because we just did that in Excel. So this is the steps you're going to take, and you know, I go ahead and annotate this, right, draw a line, shade in the relevant area, and you're good to go. You can do anything like that you want. Okay, now that you've got a little bit more familiar with using Excel and what the normal distribution can do, I want you to look at some real data. If you could pause the video for a second and try and find and open that height underscore weight data set in Microsoft Excel, then we can explore that a little bit. Okay, hopefully you have now got that open. And what I want you to do first of all is to plot a histogram of that height data. We'll just leave the weight data for right now and just do the height data. So, and because it is 25,000 records, I want to tell you this little trick to select all of them at the same time. So if you want to select an entire column without scrolling from the top to the bottom, then you can hold down the Control, Shift, and down arrow keys and then release them. And you should get everything then. And then you use Insert, Chart, and Histogram to hopefully get a picture that looks like this. Pause the video while you have a go at that. The next thing I want you to do is try out that data analysis button that we downloaded at the very, very beginning of this unit. So I want you to go ahead and find that button that we created, the data analysis button, and you're going to go to data analysis button, descriptive statistics. That is going to be where you can find your mean and your standard deviation. And then the other interesting things that you might see there are the minimum and maximum values, and that'll tell you the range of your data. I want you to then go ahead and practice by doing all of the things we just did, but for the weight data. So I want you to do the histogram, and I want you to find the descriptive statistics. Okay, so I want to spend a little time on this slide because it quite nicely combines a lot of the things we've been learning about over the last few slides with the normal distribution. And it's going to use the height data that we used already in Excel. And I'll read this to you. An airline has a requirement that cabin crew must have a height between 63 inches and 74 inches. And this is so that they can reach the overhead lockers and have access to important safety equipment on board. We're going to convert these values into a z-score. Looking at the data we have for heights in Excel, find the percentage of people who will meet the height requirement to work on the cabin crew. So what I've done here is I have copied over the mean and the standard deviation from the summary statistics data that we calculated on the previous slide in Excel. And of course, I have drawn a little graph, which is what I always do, as you know. So you do your little normal distribution curve, label the mean 67.99, and then this 63 and 74 is right here from the question, 63 inches and 74 inches. And as you know, the area that we calculate will always be all of the area to the left of each of these values. And if you want to find between 63 and 74, the best way to do it is to calculate all of the area under the curve using the 74, and then all of the area under the curve using the value of 63, and then subtract this area under the 63 from all of the area that you calculated here. So we're going to have to do a few steps. We'll use this formula for the standardization that we used before. Z equals 74, this is the x, 74 minus the mean 67.99 over 1.9. That gives us a Z score of 3.1632. This makes sense because if you remember, if you standardize information, then the mean would be 0 and this would be a positive number. You can see it's quite far over, so 3.16 makes sense. So when we put that into Excel, that Z-score, then we find that that yields an area of 0.9992. Okay, so then our next step is to calculate this area here. So again, we'll use the same formula. Z equals the x value, 63, minus the mean, 67.99, all divided by the standard deviation. That gives us a Z-score that's negative, minus 2.6263. Of course, again, we would expect that to be a negative value because it's going to be a value less than 1 because it's on this side of the mean. I mean, less than 0, not 1. This yields an area when we put it into Excel of 0.0043. And so, as we said at the beginning, we are going to subtract the 0.0043 from the 0.9992, and that returns an area of 0.9949. And what does that result mean? So if we express that result as a percentage, which of course you would simply multiply this by 100, you would conclude that 99.5% of the people from this population would meet the height requirement for the airline, so they can work on the cabin crew. Make sure you can confidently do that calculation in Excel. You can pause the video and try it out a few times and play around with some numbers. Okay, so what happens if we want to find a value from the area? Sometimes we'll be given the area or a percentage we need to find and calculate what the X value might be. So let's look at this scenario. We want to design a doorway such that 95% of people will be able to pass through without banging their head on the frame. And that is, we need to find the 95th percentile. So this time we're going to go back into Excel and use a different function. It's going to be called norm.inv. And into that we'll do the probability. That's going to be the area that we want to find, it again to the left of the number, and the mean and the standard deviation, that's just these same values we found from the summary statistics in the height data before. So we go ahead and enter all that into Excel. The probability is 0.95, that's the 95%, 67.99 is the mean, and then 1.9 standard deviation. Go ahead, open your Excel and type all that in, and what you'll find is you will return a value of 71.12. That's what you would put in your graph that you've drawn here. And it's a value that's greater than the mean, as you would expect. And I would go ahead and write that in there. And let's interpret it as well. The value of X is 71.12, and this tells us that if we design our doorway to be 71.12 inches high, then 95% of people from this population would be able to enter the door without hitting their head. For safety purposes, an engineer or anyone might like to calculate this using 99% or higher, so that the majority of people are going to be able to enter the room safely without hitting their head. Well done. We have now reached part 2 of the module on continuous probability distributions. For this second part, we will be looking at the normal probability distribution a little more. We're going to look into the 68, 95, 99.7 rule and its applications, and understand its interpretation in real-life applications. We are also going to look at the exponential probability distribution, how to recognize it by its shape, and how to understand when to apply it in real-life applications. Now, a concept that is helpful in interpreting the value of a standard deviation is the empirical rule. It's also called the 68, 95, 99.7 rule. And it states that for data sets that have a distribution that is approximately bell-shaped, the following properties apply. About 68% of all values fall within one standard deviation of the mean, as indicated on this diagram. About 95% of all values fall within 2 standard deviations of the mean. And about 99.7% of all values fall within 3 standard deviations of the mean. The empirical rule is not exactly, it's not going to ever be exactly 68%, exactly 95%. And of course, you may not get an exactly smooth curve like this. There's going to be some ups and downs going through the data. But the more data you have, the smoother the line often gets. And you may be wondering as well, what happens if I go 4 standard deviations from the mean, or 5 or 6? So I'll tell you, this line, as you can see, goes on past 3 standard deviations from the mean, and it will go on and on and on and on. It never actually touches the line. So this is infinite in this direction and in this direction. So you can go multiple standard deviations from the mean, but what you should think about is 99.7% of all of the data, all of the values fall within 3 standard deviations of the mean. So how much more information are you going to get from going any further? You might want to go 4 standard deviations from the mean. But this is just a rule you can use, and we'll play around with it in the next few slides and see what we can use this rule for. In part 1 of this unit, we looked at a dataset in Excel, which we explored in detail. Now, based on the weight data rather than the height data, we found that we have a bell-shaped distribution with a mean of 127.08 pounds and a standard deviation of 11.66. Using the empirical rule, let's try and answer the following questions. Find a range around the mean that includes approximately 95% of the weights. Secondly, what is the approximate percentage of people with weights between 92.1 pounds and 162.06 pounds? Third, what is the probability that we have someone with a weight of more than 162.06 pounds? Okay, if you wish, some of you might like to pause the video right here and have a go at these before we move on to the next slide, where I'll show you how to calculate these. Looking at our first question then, we want to find a range around the mean that includes approximately 95% of the weights. Now, if we look at the empirical rule, we know that about 95% of all values fall within 2 standard deviations from the mean. So we've written a little formula here, mu, which is the mean, plus or minus 2 standard deviations. And then we just plug in our mean from our summary statistics and our standard deviation. So we get 127.08 plus or minus 2 times the standard deviation, which was 11.66. And then let's calculate out this bracket or parentheses. So we have 127.08 plus or minus 23.32. And then what we do is we do 127.08 minus this value, and that's our first parameter. Then we can do 127.08 plus this value, and we get the upper parameter. And therefore we can conclude that the range between 103.75 pounds and 150.40 pounds contains approximately 95% of all data. Now let's look at the next question. What is the approximate percentage of people with weights between 92.10 pounds and 162.06 pounds? So now, instead of knowing that this is 2 standard deviations from the mean, we don't know. So we're just going to put the value k in here, and then we're going to kind of back calculate it using the same method that we used before. But k is the number of standard deviations away from the mean. If you recall the last slide, that was number 2. We don't know what it is in this case. So again, we have mu, we know mu, we'll plug that right in. It's this plus or minus k times the standard deviation, 11.66. Nothing different here except the value k. So what we will do is we will rearrange this formula. And so we will take 127.08 from both sides, and we will put that right here, and then we can divide what result we get here by 11.66 to isolate the k value. So you can see what I've done right here. I've just plugged in the values. I've only done it on one side, but this should give us the value we need. So 162.06 minus 127.08 is 34.98. We divide that by the 11.66 and we get an answer of 3. And according to the empirical rule, 99.7% corresponds to 3 standard deviations from the mean. So the approximate percentage of people between 92.10 pounds and 162.06 pounds is 99.7%. Okay, moving on then. What is the probability that we have someone with a weight of more than 162.06 pounds? That was our upper value here. We know that that was 99.7%. So if we do 100% minus the 99.7%, we get 0.03%. However, be careful, this would give us an area in both tails, and we only want the upper tails because the question asks more than 162.06. So because the distribution is symmetrical, we are able to simply divide that value by 2, and then we would get a probability of 0.015%. Okay. Go ahead and play around with those numbers however you want, and make sure you get confident with how to calculate these kind of things. Okay, let's look at the exponential probability distribution. The exponential distribution is used when looking at the amount of time until some event occurs. And exponential distributions are commonly used to calculate product reliability. Some examples would be the length of time to complete a math problem, for example, or maybe you would be looking at the time between customer arrivals at a store, or the time until a geyser erupts, and you're going to come up with some average and be able to plug that right into the formula. This graph here is showing you the shape. This point here where the white intercept happens is what we call lambda. The curve starts right here and it will decrease over time. So it'll be time along the bottom, and this is your f of x up here. So we've got 2 formulas, and this is going to show you the shape of the distribution. So you've got lambda e, which is a constant, and you can find, I think if you see a calculator, it will say exp on the button, so you could use that. So lambda e to the minus lambda x, and where lambda is 1 over mu, that's the mean. The cumulative density function, written like this, f of x with the capital F, is 1 minus e to the minus lambda x. Let's look at the example of the time between geyser eruptions. This is probably the best way to illustrate these kind of problems. So the number of minutes between eruptions for some geyser can be modeled by the exponential distribution. For example, suppose the mean number of minutes between eruptions for this geyser is 25 minutes. If the geyser erupts, what is the probability that we'll have to wait less than 40 minutes for the next eruption? To solve this, we first need to calculate the rate parameter, that's lambda, and that will be 1 over the mean mu. So we know that that's in the question. The mean number of minutes between eruption is 25 minutes. We would have figured out the mean by doing something like collecting or observing the geyser for a long period of time and figuring out kind of over time what the mean is. So Someone's obviously studied that before in the past, and this is why we have the 25 minutes. So we do, it's 1/25, and that means that lambda is 0.04. And so if we were trying to label this graph, which is this is time over along the bottom, and we know that where the y-intercept is lambda, so that's 0.04. And we can plug in the lambda is 0.04 and x equals 40 to the formula for the CDF. So I guess if you were labeling the graph again, you would say 40 is time, so it's along the bottom. So you would label 40 somewhere along here, and then that would be all of the time less than 40, which is what you want to calculate. So yeah, we would just plug it in right into the formula. So 1 minus e to the minus 0.04 times 40, and we would calculate that on our calculator to be 0.7981. If you want to calculate e to the power of something, you usually press on a calculator the X button, it's EXP. If you do not have that, then I do want to let you know that e is 2.71828, and so that will give you pretty much the same answer. You will be pleased to know that in Excel you can also do this very, very easily and not worry about the formula. So it will give you the exact same result. You can use xfon.dist, and right here where you have the x, you would do, to quote that other example, you would put 40 in there, you would do your lambda value 0.04 in there, and because you're using the cumulative, you would return true. It says if cumulative is true, xfon.dist returns the cumulative distribution function. If false, it returns the probability density function. So yeah, we type that right into Excel, 40, 0.04, and true, 0.7981, same as we got last time. Thank you very much for sticking with Module 5, which is continuous probability distributions. I hope you had some fun trying out the problems and filling in any gaps in your knowledge from your previous studies in basic statistics. Thank you very much. I'm going to just show you now the references I used when producing the slide. This is a link where you would find out about using the analysis tool pack in Excel. I referred to statology.org, Statistics 3E book, Mario Triola Elementary Statistics, 12th edition, 2014, the LibreText library. This was the data I got for the heights and weights. If you did not manage to get a copy from the notes for this course, then you can, or if you're watching on YouTube, in fact, you can type this in and download the data. It's quite a large data set with many data points, so you can play around with that in Excel. And then John Tukey wrote a great book on exploratory data analysis, which I also referred to. Thank you very much. Hope you enjoy the rest of the videos produced by Statistics Without Borders.